Hello, everybody. My name is Steve Higgins. I'm the Technical Services Manager for Rolls Battery. We have a webinar starting up here in a couple minutes. If you can hear me, great. If you can't, this will be recorded on YouTube a little later, so hopefully it'll all be good. Again, I'll be starting it up again. I'll be starting it here in about 2 or 3 minutes just to make sure we give time for everybody to show up. So I'm going to mute my microphone again. Hold on a second, and you can familiarize yourself with the setup. There's a question and answer section. There's a chat section if you're using Google Hangouts. If you have questions or comments, feel free to leave them, and we'll get to them. Okay, everybody. Again, my name is Steve Higgins. This is the Rolls Battery Engineering GridTied and Battery Backup Systems and Battery Options webinar. I'm going to go ahead and start. And this is being recorded it's being live broadcast on Google Plus, and it's being live broadcast on YouTube. It's also being recorded, so you can view it at a later date if you need to. Just some things to start. Housekeeping items. The broadcast is about 15 to 20 seconds delayed. The reasons for that is that the Google Plus is converting it as I speak into a live broadcast. So there's a little bit of a delay. So if you have any questions, please go ahead and type your questions into on the side of the pane, there should be a Q&A or even a chat pane where you could type questions into. We'll get to your questions on a first come first served basis as we go, or at the end of the webinar. I've muted everybody's microphone, so hopefully we don't get an echo, or you guys aren't getting echo. Again, let me know if you are. I'll see what I can do to fix it. This one's only about 20 slides. It's not very long. So it's going to be about 25, 30 minutes at most to complete. And then probably 10, 15 minutes at the end, or whatever we need to answer questions at the end if there are any questions. I've already talked about the Hangouts on air. If you don't have access to the chat pane, you can email me questions at steve@surratt.com, and I'll respond to you directly. Speaking of my contact information, this is my contact information. My email address is steve@surratt.com. My phone number, I have a direct line, which is 902-597-4020, or a mobile number. You can give me a call if you need have any further questions. So as we go into the webinar, I've shown this screen in many presentations. That realistically in renewable energy applications, there's three main types of systems. There's the grid-tied systems, the grid backups, and the off-grid systems. The grid-tied systems are no batteries. You have PV connected to an inverter that's taking the 480 volts or 600 volt PV array, stepping it to a 120, or inverting it to a 120, 240 volt AC signal, basically selling the power directly to grid. We have the off-grid customers. Those are the folks that live out in the middle of nowhere. They're basically most of your battery companies, bread and butters. These are the guys that live out in the middle of nowhere. Utility power is too expensive to get out there, or they don't want utility power. So, and then the ones we're going to talk about today, your grid backup systems. The grid backup systems are a little touchy. Typically, it's a emotional decision. People are upset at the utility for disconnecting too often, too long. Maybe a decision where you live on the East Coast of the United States, or in a natural disaster-prone area like the Gulf states, or northeastern U.S., northeastern Canada, where you get ice storms where power lines are still non-buried power lines, and ice hangs off of them and shorts out the system, and then you lose power for a week, or 3 or 4 days. So those are the grid type backup systems that we'll be talking a little bit about today. Couple of big reasons why you would install a grid backup battery bank. First and foremost is the grid inputs are unreliable. I'll get into that here in the next few slides, but there's a big reason why it's unreliable. I mean, we'll get into that. And then, of course, there are lots of systems where customers have an existing grid tie system where they're selling power back to the utility. They've put $20,000, $30,000, $40,000 worth of product in their house on their roof, and power goes out and they have no power. A lot of folks experience that in the last few years. Hurricane Sandy, stuff, big natural disasters like that, where you see 1 to 2 weeks of power outage just because of a natural disaster. So when you look back at the history of most of the grid construction, most of the world's grids, primarily in U.S. And Europe, were built in the early 20s and the 30s. Back then, the grids consisted of what would be considered separate islands. What that means is that you had a utility company in say Seattle, and a utility company in Tacoma, and a utility company in different locations that were close, that were basically they weren't interconnected. In the 40s and the 50s and the 60s, with the advent of the larger power plants, the dams and the nuclear power plants, these islands were interconnected basically to the grid form that we know today. One of the things to look at is population. Back in the 1920s, 1930s, I mean, they're looking 1927, the world population was about 2 billion people. That population in 1959, when those grids were basically, the grids were finishing being tied up into islands, we were only at about 3 billion people worth of world population. In the last 70 years, we have gone from 3 billion, and we're pretty close to hitting, we're about 7.2 to 7.5 billion people population-wide worldwide. So one of the big things that's influenced the grid overall is population. The second thing is the amount of use. You know, in 1927, 1959, we didn't have the amount of appliances, even though they've become a bit more efficient, but we didn't have the appliances that we now have operating in most electric homes. So that's where you're going to see a lot of requests for grid-tied systems, or grid backup systems. The second reason, basically, you know, there's probably hundreds of thousands of grid cell back systems all over the world. Most of them were installed. Basically, you've got PV panels. When the sun comes up, they're selling power back to the utility. The utilities in the 5-10 years ago were paying pretty much even money. Nowadays, if you're paying 14 cents a kilowatt hour, you're lucky to get 3 or 4 cents a kilowatt hour back from the utility. So a lot of customers are trying to save some of that utility money by doing peak shaving, or adding a battery bank using the battery bank primarily, and then using the grid utility as a backup, like say a generator. In some cases, utilities, like for example, Hawaii is probably the most notable utility, is Helco in Hawaii, has pretty much written off grid-tied systems completely. It's not confirmed, but from what I hear in the last couple months, they've pretty much set November as a cutoff date. Now this target moves every once in a while, so you got to be careful with it. But you know, some utilities are no longer accepting grid-tie without some sort of energy storage system, and that's why energy storage systems over the last 2, 3, 4, 5 years have become the talk of the town. So when you get into design considerations, one of the things that most people make the mistake, a lot of guys will make the mistake, is you get the customer who comes in and they've got a 2,000, 3,000 square foot house, and they want to power the entire house, air conditioning and all. I have critical loads in quotes here, and the reason I have critical loads in quotes here is that most, you know, I mean, most marketing departments kind of cringe when you see when they see that, and the reason they're seeing that is, you know, when you define critical loads, is if you don't have the power, you don't have those loads powered up, something bad's going to happen. Granted, it's not in most situations. When there's no power, there's no power. But I call it critical loads because that's what the customer wants. They want to have those specific loads running 24 hours a day, 7 days a week, regardless of what their power situation is. So going back to the entire home systems, what you're going to need to do with most of these systems is you're going to have to break out the main panel, the load specifically in the main panel, into a critical load sub panel, and power that critical load sub panel by itself. Just to give you an example, recently I was at a site, single family home, fairly large home, about 3,500 square feet, 3 large air conditioners. They were in the Caribbean, and you were looking at almost 18,000 watts of load when those 3 air conditioners were running just by themselves. To do that, they would have need to put in a 10, 12, 15,000 amp hour battery bank to run 100% off the grid. The larger you make that system, the more expensive it is going to be. So you've got to really be careful. The bigger you make it, the more PV the more renewables you make it. So you've got to be careful with that. You've got to know how much power loads are consuming during your power outage. So if you or your customer don't know, doesn't understand what kind of power you're running, what's going to end up happening is the same thing happened for this customer that I visited. Someone came in, did an energy audit, didn't consider the air conditioners, didn't consider the pool pump, didn't consider the pool heater, didn't consider the electric stove, and so they way undersized the system. Customer gets the system installed, they start using it, batteries last a couple, 2-3 hours when they're expecting to last them 10-15 hours, and now the customer is unhappy. So you want to be careful with that. The way to do that is you really have to plan a site visit. With power to the home, you go out, put a current meter or even a data logger on the AC panel to measure exactly what kind of power you're trying to run if you're trying to do the whole home, or you isolate it with current transducers to measure the specific lines that you want to try to back up. That'll give you a decent picture about what you're doing for power. If you don't have a decent picture, you're guessing, and eventually that guess is going to come back, and as an installer is going to bite you. As a homeowner, what's going to happen is a homeowner is going to see that, going to use the system for a year or so, and then they're going to come back at you as the installer and be very displeased with the way the system is designed. Depth of discharge. For longevity and off-grid systems, typically what you do is you size for 50%. And the reason for this is that that's about where the sweet spot for cost is, if you're for cost per cycle and overall cost of batteries. The nice thing about backup systems is you typically can discharge deeper because you're not going to be cycling them very often. Most GridTied systems that are connected to a utility, say in Seattle, New York, or a major, say a North American grid, you're going to see 10, 20, maybe 30 cycles a year at best. So what you want to do, what you can do is you can put in a smaller battery bank, use it heavier while you're cycling it, and that way there's less overall investment to begin with. Going into cyclings, you have to consider the reliability of the grid. How often your utility you're going to be using that backup power. In my home, I lose, up to about 4 years ago, I lost power probably about 45 minutes to 3 hours a year, maybe 2 or 3 disconnections. Not a big deal. Over the last 2 or 3 years, with the windstorms that we've had in the Pacific Northwest, last year I lost during the winter. I lost power for 4 days. Not a good thing if you're used to having power all the time. So typically 3 to 4 times a year, small battery bank, 80% depth of discharge cycling. You're not going to need a whole lot of initial investment on the battery bank. If you have a disconnection 1 to 2 times a month, so you're looking 6, 10, 12 times a year, you may need a little bit larger battery bank. Again, you can use that 80% depth of discharge cycling. You're only going to be putting, say, 20, 30 cycles on a battery a year. That shouldn't be a big deal for design considerations. The one to watch out for is where you have a very unreliable utility. If you're having disconnections 3, 4, 5, 6 times per day, you're connected for 2 or 3 hours, then you go disconnected for a couple hours or an hour, and you're connected for a couple more hours. You're going to see a lot of 20, 30, 40% depth of discharge cycling, 3, 4, 5 times a day. You've got to have enough charging to get that battery bank to a decent state of charge. And just give you an example. You go into downtown Lagos, Nigeria, you can have 5, 6 disconnections every single day. Generally, you're lucky to have power for 6 to 7 hours a day. And what ends up happening is the batteries end up getting into a partial state of discharge, and they stay there because they're always being discharged and never really getting to that full 100% state of charge, unless the customer has a secondary genset to back up the utility. So be careful with that. If you can keep it small, again, you keep it small, you keep it simple. The longer the batteries, the longer the system's going to last, the happier your customer is going to be. Selecting the battery chemistry. Primarily Rolls batteries, we manufacture 2 types of chemistries, a lead antimony chemistry and a lead calcium. The lead antimony chemistries are great for cycling applications. They want to exercise, they want to cycle, they want to see that 100% state of charge to 30, 40, 50% state of, or actually, I'm sorry, 50, 60, 70% state of charge cycle. They like to see that. They like to exercise. Uh, Lead antimony batteries will lose capacity in slowed applications. Specific gravities, voltages will look great. As soon as you say you use a lead antimony battery and you're not exercising it from time to time, what will happen is the battery will actually lose capacity. And so when you go 2, 3, 4 years, and the battery, you go into a grid loss event, it should last, say, 4, 5, 6 hours, and it lasts an hour because you've lost capacity. So if you're going to put lead antimony batteries in a backup application or a grid tie application, where you're selling power off or you're doing something like that, it's a really good idea to exercise those lead antimony batteries. And the reason for that is that loss of capacity. Typically, what I instruct folks is, depending on how often your disconnections, if you're seeing a couple disconnections a year, once a quarter, when you do your maintenance checks, or when you do your specific gravity checks, or when you're doing maintenance general, shut off your AC input breaker, let your inverters run your loads for a couple hours, 2, 3, 4 hours, and then reconnect and use the grid to charge the batteries back up. It does a couple of things. It exercises the batteries, but what it also does is it verifies operation of your system. It verifies that your inverters and your charge controllers are charging your batteries. It verifies that your inverters are transferring from the grid properly. There's not a stuck or shorted relay or a welded relay that's not causing problems, because those things can happen, and it's a great idea to do that. It's part of the maintenance that people should be doing with their systems. The second chemistry that we manufacture is the lead calcium. Lead calcium batteries are primarily in the telecom business because they love to float. And what that means is the batteries love to sit there fully charged 24 hours a day, 7 days a week, and do nothing. So if I was, my primary battery that I typically look at when I'm looking at a backup system is I'm looking at probably putting in some sort of calcium battery. Lead calcium type battery, and the reason for that is that those lead calcium batteries are not going to lose capacity while they're in float, but they don't have the overall cycle life of a lead antimony battery. So lead antimony batteries, you're looking at 1,200 to 3,300 cycles at 50% the depth of discharge. The lead calcium batteries are going to be a little bit smaller, or about probably 60-70% of those numbers. So just, I just threw some numbers on the wall. I just spitball here. So typical estimated load consumption for a system, lighting 1.4 kilowatt hours. That's probably a little bit big. Refrigeration is probably right where it's at. In most cases, people lose power in the wintertime, so you need some sort of heating. Miscellaneous electronics, got to keep the entertainment going so that people can watch TV or do things, charge their phones, play video games, whatever, to stay on board while the power's there. Water pumping might be a little short, but in general, I'm figuring about 6.1 kilowatt hours a day. So what they're going to do is when the utilities drop, when the utility drops, you're going to use about 6.1 watt hours or 6,100 watts of consumption during these times. It's important to figure this out. Another thing to consider, if you go up and you add up all the losses that one of these systems sees, between module mismatch, diodes and connections, AC wiring, DC wiring, soiling on modules, battery efficiency, shading, your typical D-rate, most installers will D-rate down to about a 20 to 25% D-rate. Actually about 15 to 20% D-rate. The real D-rates actually, when you look at all the numbers, you're closer to about a 25 to 30% D-rate in North America, and that can be even more in developing countries, just because that is based on the efficiency of the power that's being delivered to your home. So be careful of that. We go to that 6.1 kilowatt hours load. This is a couple of ways of doing the calculations. So if I'm only running 6,100 watts of power, I'm going to add, say, 15% for assumed losses. That brings my number up to 776 watt hours. I'm going to do an 80% depth to discharge. So my battery bank needs to be able to provide 8,611 watt hours. So divide that by my nominal 48 volts. That gives me to power those loads for that time period. I'm going to need a 170 to 180 to 200 amp hour battery bank ballpark. Another way to look at it, I've always been kind of a current guy, but you've got to be careful with the current, because if you start with a current and you divide, you make your division calculations early, because you go right out of the gate and you make your division calculations. What can happen is if you go and you're planning on for a 48 volt system, and then halfway through it you decide that you want to go to a 24 volt system, you can be in trouble if you don't take in consideration. Because if you do, what will happen is the if you divide that by 24 volts by accident, and you'll be way offline. So again, these calculations come out to about the same, about 180 to so I'd be looking at about 180 to 200 amp hour with the battery capacity to do this backup. This is a relatively small system. This is powering literally, as I used to refer in the old days, lights, TV, and keeping the refrigerator or the cold beer cold. That's pretty much what you're powering. In today's world, again, most customers want to run. They want to run everything in the house. They want to run an entire 200, 300, 400 amp main panel. You're looking at pretty sizable systems to be able to do that efficiently and have the customer stay up with power. Just a couple of different products that we sell. The Rolls valve regulated lead acid AGM batteries. These are the AGM batteries. Roughly about 1,250 cycles at 50% depth of discharge. Your 80%, you're looking at 600-700 cycles of life overall. So if you're doing 20 cycles a year, you can easily get on these batteries 12, 15 years worth of life out of them, if you're properly maintaining them. These are calcium-based product, so they don't mind floating. But again, with all Rolls product, we need a little bit higher charging voltages than your standard AGM battery. This is an AGM R. It's a product that we developed for primarily Africa, Latin America, to compete with the smaller low-cost batteries. A lot lower cycle life. You're probably looking ballpark. You're looking at about 500 cycles, 400 cycles at 50% depth of discharge. 80 amp hour to 280 amp hour, 260 amp hours. So primarily in 12 volt models. Let's see here, and then the next one is our valve regulated lead acid gel, tubular gel batteries. Again, sealed construction, 2 volt. They're only available in 2 volt models from 250 amp hour, 215 amp hour, all the way up to 3200 amp hour. These at 80% depth of discharge, you'll see about 1700 cycles. If you can keep them in the 50% range, your cycles are much higher. They work in float backup applications. They also work in off-grid applications for cycling. And then last but not least is our flooded FC420s. These are the flooded calcium batteries. So if you have a customer that need a flooded solution or want a flooded solution instead of a valve regulated solution and want to do the maintenance, I've seen customers with these 15, 20 years of life. There's a little bit of maintenance when you're filling the water, but they're probably the best bang for the buck. So again, here's my, pardon me, there we go. Again, here's my contact information. I tried to keep this as short and as sweet as possible. If you have any questions, feel free to email me and reach out. I don't see any questions on the, let's see here. I don't see any questions typed into the Google Plus interface. At this point, if we have any questions, feel free to post them. I'll be more than happy to answer questions for you. Or if you want to send me an email, I'll be more than happy to answer your questions offline. Again, you can, at the end of this, it will post to YouTube. You can rewatch this on YouTube anytime you want. And we're going to have more and more of these. Actually, you'll probably have another one in a couple weeks. So thank you, and everybody have a good day.